All right, class, let's see about the derivative of the exponential and logarithmic functions. And as I said, we're not going to discuss any exponential and logarithmic function, but just simply the natural exponential and logarithmic functions. Okay, so the easiest thing to remember is that the derivative of the natural exponential function is itself. So the derivative of an e to the x is e to the x. That's just that. Of course, that could get boring, and we're not just dealing with an e to the power of x. If you remember from your continuous compound formula, and so on, we always have an e to the power of rt. So in other words, we will have a composition of two functions where in the exponent we will have some sort of a power, right? That's not just an x but a function of x. So sure enough, using the chain rule, yes, the derivative of such a composition of functions is, again, e is the outside function, so it's going to be e. The derivative of that's going to be e to the g of x, so the derivative of the outside function, times, move in and take the derivative of the inside function g of x, right? So it's good. We're going to practice that in a minute. We're not going to deal with these functions, but just as an FYI, if the base of the exponential function is not e, but it's some kind of 2, 3, 7, 1/5, whatever it is. So your function f of x is b to the power of x. Remember how we made a change of base in the last section, and I showed you how you can take any base and turn it into a base of e just simply by writing e to ln of b? Yes, because again, e to the power of ln goes away. So you're left with a b to the power of x. Okay, so then the derivative of this is just going to simply be, you leave it the same, times, move on and take the derivative of the exponent, and the derivative of the exponent, ln of b is some number, 0.6931 in case the base is 2, in case b is 2. So the derivative of some number times x is just the number itself, right? So again, remember, e and ln cancel each other out, and you're left with a b to the x times ln of b. So that would be the derivative of an exponential function where the base is a random b and not e. And sure enough, then this formula here becomes just a special case, because if the base is e, the derivative of e to the x is e to the x times ln of e, which would be 1, right? So there you go. Okay. By the same token, let's look at the derivative of the natural logarithmic function. And if you have a natural logarithmic function, the derivative of it is simply 1 over x. So that's a new formula, and it's fairly easy to remember. The derivative of the natural log of x is 1 over x. Now, of course, sure enough, we can extend this formula to the derivative of a composition of a natural log function with another function, because again, inside this natural log, we're not always just going to have an x. It could be some other type of function of x, right? So sure enough, the derivative of a composition is you take the derivative of the outside function, which in this case is the natural log. So it's going to be 1 over whatever's inside, which is g of x, times, move in and take the derivative of the inside of this function, right? So g of x. So sure enough, many times you see this written as, because it's 1 over g of x times g prime of x, again over 1. So this guy's going to go on the top, and the g of x will be left in the bottom. So sure enough, if you want the formula of what happens if the base is not L, but some kind of function, some kind of base with B, let's say. And again, we're not going to deal with that. Now, according to the change of base formula, we can take the log with base b of x and turn it into an ln of x divided by ln of b, right? So that is our change of base formula, okay? So now if I take the derivative of f of x, I can look at it in terms of natural log functions, which we already have a formula for. I'm going to rewrite this though a little bit so I don't have to use the quotient rule. So I can write this as an 1 over ln of b times ln of x. And again, this is a coefficient, right? It's a number. Whatever, if the base is 2, then this number would be 1 over ln of 2 is, again, 0.6931, right? So it's just a coefficient, which makes it easy because then the derivative of some number times a function, we keep the number, that's the coefficient that we keep up front, times the derivative of ln x is simply 1 over x. Okay, so there's the formula for the derivative of a logarithmic function where the base is not equal to 1. Okay, and sure enough, if you have a log with base e, right, in other words, a natural log, then it's going to be 1 over ln of e, which is 1, so that's 1 times 1 over x, so the answer would just be 1 over x, right, so the derivative of that. Okay, so now let's move on and practice these rules. So I have a whole page here of finding derivatives of exponential and logarithmic functions. All right, so let me just get a little bit organized here. Keep a visual of it. So what is the derivative of e to the 3x? So the formula says, again, don't forget to tell me that you're now about to find the derivative, so do write f prime of x. So the derivative of an e function, remember, is itself, so it stays the same, times, we took care of the e part. Now move on to the exponent. So the derivative of 3x is just the 3. That's it. So sure enough, we like coefficients or numerical factors at the front, so we throw the 3 at the front, and that's that. So let's try this. So again, it's an e to some kind of power, okay? So we'll just keep it the same. Times, move in and take the derivative of that power. So what is the derivative of x squared over 4? Remember, this x squared over 4, you can look at it simply as a 1/4 times x squared, right? The over 4 is really a 1/4 coefficient. So the derivative of that would be 1/4, keep the coefficient, times the derivative of x squared is 2x. So putting this together, sure enough, that's going to be 1/2 x times e to the x squared over 4. It's not that we couldn't have left the 1/2 x factor behind, but it looks prettier in the front. Okay. All right. Now this function here, if you really pay attention, there's actually 3 functions chained together. It's the exponential function on the very outside, then it's a square root function, so in other words, a power function of 1/2. And then when we're done with that, we still have to take the derivative of 2 times x, so that's your third function. To make this a little bit easier, again, as usual, we're going to rewrite our square root as a 1/2 exponent. So let's see what the derivative turns out to be. So the derivative, the exponential function is the outsidemost function. So the derivative of any exponential function, first of all, is itself. So that's going to stay that way. Times, move in and take the derivative of this function here. So that's going to be a power rule. So that's going to be 1/2 times 2x to the negative 1/2. So we're done with the power. Now times, move on the inside of the parentheses and take the derivative of 2x. So what's the derivative of 2x? That's just the 2. Okay. So now combining all this, putting it prettier together, let's see what we're going to get. I have no room for it. Well, sure enough, 1/2 and 2 go away. This is going to have a negative exponent, so we don't like that, so we're going to have to fix it. So I'm going to have an e to the, I'm going to rewrite this as a square root of 2x, if anything, just to save some space. So that's this, and this factor is going to go on the bottom as a 2x to the power of positive 1/2, so that's going to be a square root of 2x itself. All right, there's your derivative. Okay. Okay, I should make myself some room and not squish in. Okay, so what's the derivative of this? Well, should be easy. The derivative of a sum, you go term by term. Okay, so the first term is e to the x. What's the derivative of e to the x? Sure enough, that's just e to the x. Plus, what's the derivative of x to the 6? Not to confuse things, this is an exponential function. Yes, the variable, one second. The variable is in the exponent. However, this is a power function. The variable is in the denominator. So x to the 6, its derivative, as always, is 6x to the 5th. Minus, this is the tricky part. You have an x times e to the x. So this part alone, you're going to have to use the product rule for. Okay, so what does the product rule say to do? It says to take the derivative of the first factor, which is 1, times e to the x, plus, leave the x alone, times, take the derivative of the second factor, e to the x, which is itself. Now, don't forget, I had a minus, and this minus belongs to the whole thing, so don't forget to distribute the minus to both terms that follow. So to combine this a bit, I'm going to get an e to the x plus 6x to the 5th minus 1 times e to the x is e to the x, and then minus x e to the x. So sure enough, I got some like terms here. I'm going to cross them out. So the answer is going to be 6x to the 5th minus x e to the x. All right. So same thing, if you look at the next exponential function problem, this also is a product rule. So remember how I was saying back in chapter 1 when we learned about the product rule and the quotient rule, that for the most part we were able to avoid the product rule in the first chapter, because whatever was multiplied together in that chapter was just some polynomial functions that we can easily multiply, right, by distributing. So we were able to avoid the product rule many times. But I had said once we get to chapter 3 and we add in exponential and logarithmic functions, well, we can't multiply these. These are different types of function. And e to the x times 3x to the 4th, well, it's just that. There's no simplifying it. So then we obviously need to deal with it. So it's a product rule again. I'll write it down. Okay, so what does the product rule say one more time? It's the derivative of the first, and the derivative of e to the x is itself, times 3x to the 4th minus 5x squared plus 3. So it's the derivative of the first times the second, plus, leave the first one alone, times the derivative of the second factor. So the derivative of the second factor is a 12x cubed minus 10x. All right? And that's fine enough. However, if you want to make it prettier, what you could do, see how you have an e to the x common factor into both these products? So what you could do is you could factor it out from both, and then it's an e to the x times 3x to the 4th plus 12x to the 3rd minus 5x squared minus 10x and plus 3. And the reason why I wrote it in this order is because I mixed them so that when you add polynomials or a bunch of terms, of course you can change the order, and the way we like polynomials to be written is in descending order of exponents. So that's that. Okay, well, let's try some logs. So what's the derivative of a logarithmic function? So the rule says it's 1 over whatever was inside the log. So it's 1 over 2x times this is a composition of two functions. So we took care of the log. All it does is just takes the reciprocal of what is inside it. We call this the argument of this logarithmic function. So it's 1 over 2x times the derivative of the inside. And what's the derivative of 2x? Well, that's just the 2. So sure enough, these 2's are going to cancel out, and you're left with 1 over x. Now I'm going to show you on the side what else I could have done. And this is easy enough so you don't need to fix it. But I just want to bring back something that we've learned in the last section. Well, just because we learned it, so might as well use it. So we learned that the log of a product splits into a log of the first factor plus the log of the second factor. So if you look at the function this way, what would be its derivative? So the derivative of it is going to go term by term. What's the derivative of ln 2? Now remember, this is just the constant. There is no x in it. So the derivative of any number, again, by the way, what number is this one? It's 0.6931, right? We're using it so much, started memorizing it. So the derivative of this number is going to be 0, yes? Plus the derivative of ln x, well, that's a variable factor, right? Or a variable term. So the derivative of ln x is 1 over x. So sure enough, we end up with the same answer as up above. Okay, let's try this. Same thing. What I see here is a product between two functions I cannot multiply together. They're different types of functions. So we'll use the product rule. Okay, so the derivative is going to say it's the derivative of the first factor and the derivative of each of the x's itself times, leave the second factor alone, plus leave the first factor alone, times the derivative of the second factor, in other words, ln x, and the derivative of that is just 1 over x. That's it. There's really, we can't multiply these, we can't multiply these. These are totally different types of functions. If you want, as I said, you could factor out the e to the x as we did up above. That's fine. But either one of those answers is correct. Okay. Now, what rule are we going to use for this problem, which also cannot be simplified? And you guessed it correctly, it's the quotient rule. Okay, so what does the quotient rule say? It's the derivative of the top. And what's the derivative of the top? Well, 1 over x times the bottom minus, sure enough, leave the top alone, times the derivative of the bottom, which is 2x plus 1. And just so you won't get tempted to think it's an x times 2x plus 1 inside the log, no, it's the log function that you're multiplying to this. All over the denominator squared. Okay. So I'm going to fix this a bit. If anything, I can't have fractions inside fractions. So what is 1 over x times this parentheses? I'm going to distribute it to each of the factors up here. So 1 over x times x squared is just an x, plus 1 over x times x, that's a 1. So there you go. You don't need any more parentheses or anything. We'll distribute that. Minus, these two guys still have to be multiplied. And as I said, you could distribute the 1 times ln x and 2x times ln x if you want. But I'm just going to leave it alone. And there you have it. Okay, the reason why I bring this factor up front is to be sure and for everyone to know that it's the log value of x that I'm multiplying to 2x plus 1 and not x itself. Okay, all right, so let's take the derivative of this. So what's the derivative of this function? Again, it's a composition of two functions. The natural log is the outside function, and on the inside is some polynomial. So the rule says the derivative of a log is 1 over whatever's inside that log. So it's just the reciprocal of that. Times, move on and take the derivative of what's inside. And the derivative of what's inside is a 2x minus 5. And again, you're multiplying it to the whole 2x minus 5, so I'd put parentheses around it. And this is just fine the way it is, but it looks better if you just multiply it to the top. And then just write one fraction out of it. Again, because that's a 2x minus 5 over 1, yes, so this gets multiplied to the top, this gets multiplied to the bottom. So it's kind of what I wrote right here, that you do have the derivative or the reciprocal of what's inside, right? The derivative of ln of some function of x is the reciprocal of that times the derivative of the inside. And what we like to do is we like to make a fraction out of the whole thing. So put this at the top. Okay, last one. So let's think about what we could do here. This is a product, yes? So we're going to use the product rule. So the product rule says, take the derivative of the first factor, so 4x cubed times ln x, plus, leave the first factor alone, times the derivative of ln x is 1 over x. Now, this very much looks like a composition of two functions, but if you think about what we just learned in 3.2, maybe we can make our lives a lot easier, because what is e to the ln x really equal to? This part just equals to x. So then I don't need to deal with compositions of functions, and the derivative of x is just the 1. Okay, so I'm just going to combine this a bit for you, because x to the 4th times 1 over x is x cubed plus 1. And that's again the derivative of e to the ln x, which is just an x. Okay? All right. So we're going to take a break, and I'm going to upload this video and then make another one.